Hello students, welcome to today's session. Today we shall be discussing some important questions based on the reagents used in organic chemistry. So this particular session would be helpful for those who have done organic chemistry once complete, and also would also be helpful for those students who do not know how to use this particular topic of reagents in the reactions, that they are scared of, that how to apply the information related to reagents. So some of the questions which we are going to discuss in today's session, by which you are able to understand some of the reagents, and I shall be placing few more videos in regard to this particular topic of reagents, because in organic chemistry there are good amount of reagents available in R plus 1 plus 2 syllabi. So here comes the first question. Here what you are supposed to do is that identify the correct sequence of reaction. You need to tell which out of this is a correct, or the during this sequence of reaction the final product which we are obtaining, is it correct or not. That is what the endeavor is. So let us take up one by one each of these options. First option is this: you are being treated with aldehyde or ketone or carbonyl group, and you are being treated with CH3 MgBr. So this is the first reagent which you should know. This is called as Grignard's reagent. This is called as Grignard reagent, and this Grignard reagent is a sigma bonded organometallic complex or organometallic compound, where you have a direct bond between carbon and metal, that is magnesium, and this in a way is a covalent sigma bonded complex, but this is quite a polar one. This is delta positive, this is delta negative. You may say that Grignard reagent is a source of carbanion. This is a source of carbanion. So first, in today's session you should remember that Grignard reagent is a source of carbanion. This, whenever this sigma bond would break, it would break heterolytically like this and just generate a CH3 negative. Then now first let us do that. This CH3 negative is going to attack this carbonyl group. This goes here. So as a consequence of this, you would get a structure like this. So from here you would get a negative, and this is the CH3 which you have attacked. So if I place it here, that we happen to move from this side to this side. So this is what we have done. Now the counter ion for this would be, along with it, is the MgBr. So this is the counter ion, and on hydrolysis, if you do its hydrolysis in acidic medium, so what it would generate is a alcohol, and what type of alcohol is being generated is a tertiary one. And here what you end up getting here with the loss of hydroxy magnesium bromide. Now what you have generated is a alcohol. Now this particular alcohol is treated with SOCl2. Now this is another reagent which you should remember, that SOCl2 is a thionyl chloride. Now there are two ways to use it: thionyl chloride with and without pyridine. There are two ways, but here, because I just have to tell you how this reagent is to be used, you can simply take up this shortcut, that although there is a quite a good amount of mechanism involved in it, at this point of time I just would tell you to remember it like this. So RCl SOCl2, so what are being generated? RCl SO2 and HCl. In, as a matter of fact, when you happen to treat this particular compound, which we are going saying it as alcohol, if it is treated with SOCl2, what you end up getting here, you would get here a alkyl halide along with SO2 gas evolving out, and HCl gas also is evolving out. Now this SOCl2 happens to react with the given alcohol in two ways: with pyridine and without pyridine. There is a concept of inversion and retention of the configuration, but it is, I shall not be using this, because then I'm not able to discuss all the reagents available in today's session. So what we end up getting here is alkyl halide. So once you get the alkyl halide, so we reach this point. So what is A? A we got is this one. This is alkyl halide. Now this alkyl halide is being treated with tertiary butoxide. This is basically tertiary butoxide ion. Tertiary butoxide ion. Tertiary butoxide is a sterically hindered base. This is a sterically hindered base. This is a new reagent, or potassium tertiary butoxide you can say, or sodium tertiary butoxide it is. So this tertiary butoxide is a sterically hindered base. Sterically hindered base. Just we people have hindered base. Just we have used this particular reagent number of times, that is alcoholic KOH. Alcoholic KOH when heated with alkyl halide happens to do dehydrohalogenation. This tend to do dehydrohalogenation, that one halogen and one hydrogen of alkyl halide goes out. So on the same note, this alcoholic KOH is KOH dissolved in ethanol. So here the KOH is being dissolved in tertiary butyl alcohol, tertiary butyl alcohol, and this tertiary butyl alcohol has to, now what is the difference between if I take alcoholic KOH? Alcoholic KOH is a source of ethoxide, basically potassium ethoxide, but here it is tertiary butoxide. Tertiary butoxide is a sterically hindered base. So now what it would do, it has to undergo, so you have to remember, when you have a butoxide heated with its particular alcohol, or alcoholic KOH is heated with alkyl halide, you have to do the dehydrohalogenation. So this particular reagent, either this or this, is a reagent which is used for dehydrohalogenation. And dehydrohalogenation happens like this. This is alpha carbon, and here you have this as beta, this also is beta, but this is beta dash, and beta beta which I have shown is chemically identical. So there are two ways to remove the hydrogen. What we are saying is that one way of removing hydrogen, that is the beta hydrogen, I can remove it from here. One side is this is the beta, another is this beta dash. Now what we have to remember here is, when you are using tertiary butoxide, that is sterically hindered base, sterically hindered base can approach the beta hydrogen from a less hindered site. So it can deprotonate a hydrogen from a less hindered site, resulting in the formation of this type of a alkene, this type of a alkene. So what alkene do we get here is something like this. This would be a major alkene. This would be a major alkene if you are using tertiary butoxide, sterically hindered base. Had you been using alcoholic KOH, which is not that sterically hindered, in that case this beta hydrogen could also be removed out. In that, what we may get is something like this. So but here what they have shown with tertiary butoxide, they have shown the major product is this. So this in a way is a wrong narration. So this, the A option would not be the right one, so this is a wrong one. Now moving on to the B part. Now let us check what is B part. The starting material of B part is what you call it as adipic acid. So I may take it as this is nothing but adipic acid. Now adipic acid is being heated. So here you should remember there is a topic of Ohm's gap. Ohm's gap. So this basically is the case of dioic acid. So dioic acid, first is oxalic acid if I write it. Oxalic acid, then malonic acid, then succinic acid, and so on. Then glutaric acid, and adipic acid, and so on. So basically all of these acids when are heated, they undergo some sort of, this is last one is palmitic acid. So when you heat it, so what shall you be getting? So we are at this point of time at this stage, that is adipic acid. Now when adipic acid is heated, it is undergone heating. So what would happen is this water and 1 mole of carbon dioxide goes out. Heating adipic acid, that is the case of one, this is 1,6-dioic acid, and here you have this as to 1,2-dioic acid, 1,3-dioic acid, 1,4-dioic acid, 1,5, 1,6, and 1,7-dioic acid. So all of these dioic acids when heated, they give different results. Say for example in the case of malonic acid, if you heat it, malonic acid undergoes decarboxylation. So this loses carbon dioxide. Succinic and glutaric acid undergoes dehydration, and adipic and palmitic acid on heating undergoes dehydration as well as decarboxylation. And last but not the least, the case of oxalic acid, if you talk of, during oxalic acid, whole of the molecule get decomposed. This is the oxalic acid. If oxalic acid is being heated, so here you would end up getting this water, this carbon dioxide and carbon monoxide, everything goes out. So carbon dioxide, carbon monoxide and water goes out. And in the case of malonic acid is the case where you shall be losing carbon dioxide only. Why is it so? That there is a detailed mechanism for that also. We shall be doing in some other video, or today only in some question I shall be doing it. And in the succinic acid, succinic and glutaric acid, it would lead to anhydride. Let me show it to you. Succinic acid, if you have a succinic acid and you have heated it out, so this water goes out and you would get succinic anhydride. This is a very popular one. This is succinic anhydride. Similarly, you can get glutaric anhydride. But in case of adipic acid, you would end up in last two cases, you would end up getting cyclic ketone. You would end up getting cyclic ketone. So the matter of the fact is that in the first case, if I write it, that on heating this water and carbon dioxide goes out, resulting in the formation of cyclopentanone, type like this, or rather I should draw it like this. It would give you cyclopentanone. You can draw it like this, cyclopentanone. Now this cyclopentanone is then treated with phosphorus halide. This is a very important compound. This is called as halide. This is a new reagent for this, and this is a part of a very popular reaction which we call it as Wittig reaction. So now let us understand this reagent also. What does it do? This is a reagent which converts a given ketone into alkene. This is the fact of the matter, that this particular reagent converts a given ketone into a alkene. Just let me do it first for you, then we'll explain it. That if in case I have used this particular reagent here, so what it shall be doing, this is triphenyl phosphine, and this basically would take out this one and you end up getting this alkene. So here the answer is not the one they have written, so this option is also wrong. But how do we get that? Let me explain it in a while. So what, how does Wittig reaction happens? First, how does this Wittig reagent is formed? Wittig reagent is formed. This is very important to tell you. So first you take triphenyl phosphine. This is triphenyl phosphine which is having a lone pair. It is being treated with alkyl halide or alkyl halide or bromide, whatever you can take. So this would hit it. This is basically a SN2 type of nucleophilic substitution where you end up getting this compound. So phosphorus would get a positive charge. This is CH3 and the counter ion is Br negative. Now into this particular system, if you add some base, if you add some base or like alkyl lithium, where this is a source of carbon ion, so this carbon ion or any base would abstract this H, resulting in the formation of this particular compound. And this would become negative, sorry, here it should be written as negative, you would get this reagent. Now this reagent is in a way is a source of carbon ion, and this is what you call it as Wittig reagent. This I may say it is a source of carbon ion. Source of carbon ion, just like Grignard, it also is a source of carbonate and it can be resonance stabilized also. So this particular reagent which we have written is what you call it as Wittig reagent. This in a way is said as Wittig reagent. Now, how does this Wittig reagent helps to produce the one which we are showing, the one we are going to see, that what happens is this Wittig reagent, if I happen to show you like this, what basically it is going to create, whenever you have any aldehyde or ketone, or rather I would show it like this, if you have this particular reagent, the hybrid of this would have, this has to be delta negative, this has to be delta positive, because there is a resonance taking place between these two. So the carbon which is CH2 is having delta negative charge, and if I would show you that this is the ketone which we have, and this aldehyde or ketone, and this has delta positive, This is delta negative, this is delta positive. So first the dipole-dipole interaction would happen here. So this dipole-dipole interaction would bring them together close to each other. Now what happens is, then this goes here, this goes here. There is a formation of this type of a intermediate stage is being generated, and this intermediate stage at times is called as betaine stage. This is called as betaine stage. Betaine stage. Now lastly what happens is, then this bond opens up like this goes here, this goes here, and you end up getting this compound, triphenyl phosphate. This can be said as oxaphosphetane, and along with it you would also be getting CH2 double bond C this. So this is what you have done. So one of the CO group has been replaced by this CO group has been replaced by CH2 group. This is what you have to remember in this particular case. So this particular group has been changed. So this is what the role of Wittig reagent is. And similarly, if I would place it here for you, that if I create a system like this, that if you have, similarly you could have a sulfur halide also. Here is one difference in the case of sulfur halide. What does this sulfur halide do? So if on the similar pedagogy, if I take this as to be dimethyl sulfide is being treated with alkyl halide, first the nucleophilic substitution happens because sulfur is having a lone pair, so you end up getting this sort of a moiety, and along with it is the counter ion. Now into this, if you add some base, that base would abstract this H positive, resulting in the formation of the similar type of a entity which we used for the phosphorus. So here you would get CH2 negative, and this was sulfur positive. So this moiety is again a source of carbon ion. So this is what you call it as sulfur halide. Only difference in this case is, when this sulfur halide is going to attack the aldehyde or ketone, just like the one we have shown in the previous case. So here what would happen is, this CH2 negative sulfur CH3 CH3, so this is positive, this is going to attack it, this goes here. So as a consequence, what you end up getting here is something like this. So this oxygen get a negative charge, and here you have CH2 and sulfur as positive and CH3 CH3. Only difference here would be, unlike the previous case, in the previous case, why this reaction happens this way, the driving force here is the driving force in this reaction is the bond energy of P double bond O. The strong bond energy of P double bond O drive this reaction this way, that oxygen wanted to get attached with the phosphorus. The driving force is this. But in the case of sulfur, the bond strength is not that much. In this case, what happens is it undergoes intramolecular nucleophilic substitution type of a thing. So this oxygen attacks it, and this goes out, resulting in the formation of epoxide. So if you use what you call it as sulfur halide with aldehyde and ketone, it would convert carbonyl group of aldehyde or ketone into a epoxide type of a thing. So that is the only difference between phosphorus and sulfur halide. So I think this reagent is also clear to you. Moving on to the one which we have just started with is this one. So this also is not generating the thing which we are seeking for. Now next would be, let me show it here only, next structure, or rather I would make it here only. So next C option is, you are using lithium aluminium hydride. So lithium aluminium hydride is actually a source of H negative hydride ion. So again it would have a, all of these reagents are having a mechanisms, but here what I'm telling you is simple way to explain the things. So this goes attacks this as a uh, as a nucleophile, and this is what you call it as nucleophilic addition. So nucleophilic addition has happened, so H goes here and this goes here, and the counter ion is the lithium moiety. Now once you do this, then there is a role of a solvent. In the second step, the water gives its H positive to this, and as a consequence what you end up getting here is something like this. So on one side you generated H, which came from the lithium aluminum hydride, and on other side you generated H. This came from the water. So this came from the solvent, and this comes from the reagent. That reagent is lithium aluminum hydride. So what basically we are going to do in this particular problem, you are being treated with this particular compound, and this is being treated with lithium aluminum hydride. So H negative is of course is going to attack it. This goes here, followed by the addition of water. So you would end up getting alcohol. Now what type of alcohol it is? It is tertiary, it is secondary alcohol. Now this secondary alcohol is being treated with concentrated sulfuric acid. Now again, concentrated sulfuric acid when heated with the alcohol would give you a dehydration product. So make it a point here, you have to remember this particular reagent, that it's concentrated sulfuric acid along with heating is going to give you uh, dehydrated product. So now how to do it? This is the starting material where you have this species, and this is being treated with H positive, and this lone pair attacks it. So first you would get the protonated alcohol. That is very simple to understand, protonated alcohol, and this protonated alcohol then throws this out as water, resulting in the formation of carbocation. Now this particular carbocation is the carbocation of the type tertiary or secondary, and this secondary carbocation, if got a chance to become a tertiary, it would want, and that is possible if you do the hydride shift. So once you do the hydride shift, you end up getting this particular carbocation, which is tertiary, which is now tertiary in nature. And here comes the hydrogen. And the last step, which you all know, during the dehydration, the H positive which we added has to be abstracted. And which hydrogen I should abstract now is the beta 1. So both of these beta are identical. This is beta dash. So beta dash would generate alkene which is less alkylated. So I would do the dehydration from here. So if I do the dehydration from here, I would end up getting this type of a alkene. And this alkene versus if you have gone for this beta hydrogen, that is the one I'm marking it with green marker. In that case, you would have generated this alkene. So there are two ways to do it. One is this one, another one is this. So there is regioselectivity possible, that there are two ways going here. One to the A part, another to the B part. We shall be saying A is a major product because dehydration of alcohol would end up giving you alkene which is in accordance with Setzeff, or which is more alkylated, because it would have more hyperconjugative hydrogens, and that too, and the reaction has gone through the carbocation mechanism, so it would reach to a product which is very stable. You may say it has adopted E1 type of elimination. So here we are thinking that this particular reaction happens to be the correct one. Let us check this out. Yes, I think this is the major product which we got. And the last part which we are left with is also very important. So what you have started with in this particular case is a now you have to be little vigilant while seeing this particular starting material, because first the heating is being done. During heating, what you are going to do is, this is a case of beta keto acid. Beta keto acid is a type of a species where you can draw it like this. This is what you call it as beta keto acid. So this beta keto acid, for this the video is already there on the channel. You can go through that. This beta keto acid, this is alpha, this is beta, this is have a special property of going through a chelation type of a transition state. So what basically it does is, this goes here, this goes here, and this goes here. As a consequence, what you end up getting here is something like this. So you would get OH here, this would become CH2, and carbon dioxide goes out. This is basically decarboxylation, and this is nothing but enol, which would undergo tautomerism to give you what you call it as ketone, so, or aldehyde. in this particular case it is ketone if I have taken started with R part. So the point is that this particular species, because this is alpha, this is beta, so decarboxylation would happen. So this decarboxylation results in a ketone. So the first part which we got here is something like this. Let me show it here on this side. So we end up getting this product. So here you have a CH3 and this would remain as such. So you get decarboxylation has happened, you get this particular type of a ketone, and now this is being treated with lithium aluminum hydride. So lithium aluminum hydride is a source of lithium aluminum hydride is a source of H negative. So this would attack here followed by protonation. So basically you end up getting this particular type of a alcohol. So you get this alcohol, and this is the same product or same starting material which not one of the intermediate step of the previous reaction. In the previous reaction this type of alcohol has came into the picture, and on treating it with concentrated sulfuric acid, again you wanted to do the dehydration. So concentrated phosphoric acid or sulfuric acid could be a choice of reagent for doing the dehydration. So here also you would again would get the reaction through the formation of all those steps which we have already done, and here you end up getting this as to be the major product, CH3 and this one. So this particular product should have been formed, so they have showing is something else, so this would not be the right case. So the steps which we used in this particular thing is already being shown in the previous case. This is what we have started with. This is the same reagent which was there. This is the same starting material which was there in the slide in the D option. The A part is nothing but the same starting material. So I think the one question which we have done in today's session have given you good amount of understanding of some of the reagents. So what are the reagents? Let's consolidate what we have read. We have read about RMgCl, that is Grignard reagent. Then we also read about tertiary butoxide, what is the role it undergoes dehydrohalogenation through a side which is less alkylated. It is going to give you alkene less alkylated. Then we talked about the topic of 1,2 or dioic acid, that what is the effect of heating on to the dioic acid. And we also learned about Wittig reagent. So good amount of understanding came about the different reagents. Then we also left understood the meaning of lithium aluminum hydride. This is a source of H negative. H negative comes from the reagent and the solvent would give you H positive. And we also have read about what is the role of heating during beta keto acid. It is going to do the decarboxylation. And lastly, concentrated sulfuric acid and phosphoric acid are the source which would do dehydration of alcohol, and that alkene would be formed which is more alkylated. I hope you have understood today's session. Thanks a lot. Have a nice day. Stay safe. And in upcoming session, we shall be making some more videos pertaining to this particular reagents section. Thanks a lot. Have a nice day. Stay safe. Take good care of yourself.